Welcome to The Midnight Physicist. In today's video, we're diving into one of the most mind-bending phenomena in the universe, the merger of black holes. When two black holes collide, they create powerful gravitational waves that travel across space and time, providing us with an entirely new way to study the cosmos. Join us as we unravel the science behind these cataclysmic events, explore how we detect them, and discover what they can teach us about the universe. Let's jump into the science of the unimaginable. Have you ever looked up at the night sky and wondered what happens when the most powerful objects in the universe collide? Stars are spectacular, but imagine something far beyond them. Black holes. These invisible giants are regions in space where gravity is so intense that not even light can escape. Despite their invisibility, black holes hold some of the most fascinating secrets of the universe. Now picture this: two black holes, each millions of times more massive than our sun, locked in a cosmic dance. They orbit each other, slowly getting closer, creating ripples in space-time, gravitational waves. When they collide, reality itself shudders. Time and space bend, and a new singularity is born. The question is, can two black holes merge into one? And if they do, what happens afterward? This isn't just theoretical. Gravitational waves have been detected, confirming that black hole mergers are real. Using LIGO, scientists observed the first black hole merger in 2015. These discoveries have revolutionized how we understand the universe, offering insights into gravity, space-time, and the evolution of galaxies. Before diving into mergers, let's first understand what a black hole is. A black hole forms when a massive star collapses under its own gravity, creating a singularity, an infinitely dense point. The area around it, where no light can escape, is called the event horizon. Contrary to popular belief, black holes don't suck things in like a vacuum. They bend space-time and pull objects toward them. There are three types of black holes: stellar mass black holes, supermassive black holes, and intermediate mass black holes. Stellar mass black holes form from large stars and are up to 10 times the mass of our Sun. Supermassive black holes reside at the centers of galaxies and are millions to billions of times more massive. Intermediate mass black holes are in between, but remain largely mysterious. Now, let's focus on black hole mergers. When black holes are in a binary system, they orbit each other, gradually losing energy as gravitational waves. Over time, they spiral inward and merge, forming a new, more massive black hole. This process releases immense energy, which we can detect. In 2015, LIGO detected gravitational waves from two black holes merging, each about 30 times the mass of the Sun. During the merger, the event horizons combine, forming a new black hole. This new black hole is slightly less massive than the sum of the originals, as some mass is converted into energy and released as gravitational waves. The waves carry data about the black holes, including their mass, spin, and distance. Scientists use this data to test Einstein's theory of relativity and explore the universe. Black hole mergers not only reveal details about black holes, but also provide insights into galaxy formation, gravity, and space-time. In the next segments, we'll explore these fascinating events further and uncover their significance in the universe. When two black holes are in a binary system, they begin a slow but inevitable journey toward each other, driven by their mutual gravitational attraction. At first, the black holes orbit each other in a stable dance, but over time, they lose energy. This energy loss is due to the emission of gravitational waves, ripples in the fabric of space-time itself, caused by the motion of massive objects. As these black holes orbit, their gravitational waves carry away energy from the system, causing their orbits to decay gradually. It's a process that might take millions to billions of years, but eventually, the black holes begin to spiral inward. Gravitational waves were first predicted by Albert Einstein in 1915 as part of his groundbreaking general theory of relativity. According to Einstein, massive objects like black holes don't just exist in space, they distort the very fabric of space-time around them. When massive objects move, they create ripples in space-time, similar to how a stone dropped into a pond creates ripples across the water's surface. These ripples travel outward at the speed of light, and just like water waves, they carry energy across vast distances. It wasn't until 2015 that scientists were able to directly detect these waves, confirming that gravitational waves are real. The Laser Interferometer, Gravitational Wave Observatory, LIGO, was able to detect the faint signal caused by the merger of two black holes. This momentous discovery opened up an entirely new way to observe the universe. Instead of relying on light, scientists could now listen to the universe's most violent and energetic events, like black hole mergers, through these ripples in space-time. As the two black holes spiral closer together, their motion becomes increasingly rapid. Their gravitational pull strengthens as they lose energy through gravitational waves, and they begin to spin faster, like ice skaters pulling in their arms. At some point, they reach the final stage of their journey, where their orbits decay so quickly that they merge into one. This merger is incredibly violent, sending shockwaves through space-time. The resulting energy release is so intense that it can briefly outshine all the stars in the universe combined. The burst of energy is not in the form of light, but rather in the form of gravitational waves, which we can detect with instruments like LIGO. The black holes that merge form a new black hole, one that is more massive than either of the original two. However, the new black hole is not simply the sum of the two original black holes' masses. Some of the mass is converted into energy and released as gravitational waves during the merger. This energy causes a phenomenon known as ring-down, where the newly formed black hole vibrates as it settles into a stable state. The entire process, from the spiraling orbits to the final merger and formation of a new black hole, takes place in a fraction of a second, but the resulting gravitational waves travel across the universe for billions of years, carrying crucial information about the merger. What makes this process so significant is that it provides a unique opportunity to test Einstein's general theory of relativity in extreme conditions. These mergers offer a natural laboratory to study how gravity behaves when it's pushed to its limits. By studying the gravitational waves emitted during black hole mergers, scientists can learn about the properties of the black holes involved, such as their masses, spins, and the distance between them. This data allows us to probe the very nature of space-time itself. The detection of gravitational waves has provided more than just insight into black hole mergers. It has allowed us to directly observe how massive objects interact under extreme gravitational conditions. These observations deepen our understanding of space-time, the nature of black holes, and the fundamental forces that shape the universe. With each new detection, we move closer to unlocking the mysteries of gravity and the cosmos. Moreover, studying these mergers helps us understand the formation and evolution of galaxies. Since black holes are often found at the centers of galaxies, studying their interactions can reveal clues about how galaxies themselves form and evolve over time. The energy released during these mergers also plays a crucial role in shaping the surrounding environment, affecting the gas and dust around black holes and influencing the growth of galaxies. After two black holes merge, the immediate result is the formation of a new, more massive black hole. However, the consequences of this merger extend far beyond the creation of this singularity. The merger's aftermath plays a significant role in the surrounding space, influencing everything from the galaxy's structure to the very fabric of space-time. When black holes merge, they generate an immense amount of gravitational waves, ripples in space-time that carry vital information about the black holes involved. By analyzing these waves, scientists can learn about the mass, spin, and distance of the black holes before and after the merger. The data collected helps refine our understanding of black holes' properties and behavior, which has been difficult to study directly in the past. Each gravitational wave signal allows us to hear events occurring billions of light years away, offering a new window into the most extreme environments in the universe. However, the merger does not just affect the black holes themselves, it impacts the galaxy and the environments surrounding them. Black holes are often found at the centers of galaxies, particularly the supermassive black holes that reside there. When black holes merge, especially in galaxies that host supermassive black holes, it can lead to the growth of the central black hole. As smaller black holes merge with supermassive ones, they increase the mass and gravitational pull of the central black hole, which in turn affects the galaxy as a whole. This process might influence the galactic dynamics, altering the formation and evolution of stars within the galaxy. A more massive central black hole could cause a change in the distribution of stars and gas, potentially triggering a new cycle of star formation. The energy released during a black hole merger is so powerful that it can ripple through the surrounding space, affecting nearby stars and gas clouds. These shock waves from the collision can trigger star formation in regions that were previously inactive. In some cases, the energy from the merger may even trigger the collapse of nearby clouds of gas and dust, forming new stars in a process known as starburst activity. These cosmic events reveal just how interconnected black holes are with their environments. What begins as the merger of two isolated black holes can spark a chain of events that affect the larger cosmic ecosystem. Beyond affecting the galaxy, black hole mergers also hold the potential to unlock mysteries about the nature of dark matter. Since dark matter doesn't interact with light or normal matter, it's nearly impossible to observe directly. However, its presence is felt through its gravitational effects on galaxies and black holes. Studying the way gravitational waves affect their surroundings could give astrophysicists indirect clues about how dark matter behaves. While we cannot directly observe dark matter, understanding the effects it has on the space around it can help us understand its nature. One of the most fascinating aspects of studying black hole mergers is that it allows us to look back in time. Gravitational waves travel through space and time, carrying information about the event that created them. The signals we detect from black hole mergers come from events that occurred billions of years ago, long before our own galaxy, or even stars, were formed. This means that by studying these waves, we are able to peer into the early universe and learn about the conditions that existed when the first galaxies and black holes were beginning to form. Each new black hole merger we observe brings us closer to understanding the cosmic past, the birth and evolution of galaxies, black holes, and stars. Gravitational waves allow us to witness the universe's history in real time, providing an unprecedented view into the universe's most extreme moments. The ability to detect these waves gives scientists a unique tool to probe the beginning of time itself. But these discoveries go beyond cosmology. The ability to detect gravitational waves has opened a new frontier in astrophysics. Each detection gives us valuable insights not only into the behavior of black holes, but also into the nature of space-time itself. Since gravitational waves are a direct consequence of the curvature of space-time, studying them helps scientists test and refine theories about the fundamental structure of the universe. By studying the waves, we can learn more about the fundamental forces of nature and the structure of space-time, which were once only theoretical concepts. The detection of gravitational waves and the study of black hole mergers are reshaping our understanding of the cosmos. These phenomena provide us with a natural laboratory for testing Einstein's theory of general relativity under extreme conditions. As more black hole mergers are observed, we are not only gaining insight into these cosmic giants, but also unlocking the deepest secrets of the universe. The ability to observe black hole mergers and other extreme cosmic events is a remarkable achievement, and it all comes down to gravitational wave detectors. The most famous of these detectors are LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo. These observatories are the result of decades of work by scientists and engineers around the world, and they are at the forefront of a new era in astrophysical research. So, how do these detectors work? At their core, both LIGO and Virgo use laser interferometry to measure the tiny distortions in space-time caused by gravitational waves. These detectors are incredibly sensitive, capable of detecting displacements as small as 1/10,000th of the diameter of a proton, a feat that was unimaginable just a few decades ago. Here's how it works. Both LIGO and Virgo have two long arms that form a giant L shape. Each arm is several kilometers long. A laser beam is split into two, with each half traveling down one of the arms. At the end of each arm, the light is reflected off mirrors back to the central detector. Under normal conditions, the beams of light recombine perfectly when they return to the detector. However, when a gravitational wave passes through the detector, it causes a tiny distortion in space-time, which changes the distance the light travels in each arm. This results in a shift in the way the light waves recombine, and the detector registers this shift as a signal. The change is incredibly small, on the scale of a fraction of the diameter of a proton, but it's enough to detect the passage of gravitational waves. Gravitational waves, unlike light, can pass through matter without being absorbed or scattered. This makes them ideal for studying the most distant and violent events in the universe, such as black hole mergers. When a gravitational wave reaches Earth, it can travel through solid objects like mountains, oceans, and even buildings without being affected by them. This allows the detectors to capture the signals from events that happened billions of light years away, even if those events occurred long before the formation of our own galaxy. The sensitivity of these detectors is extraordinary, but it also poses a challenge. The smallest vibrations from sources like traffic, seismic activity, or even wind can create noise that interferes with the signals we're trying to detect. To overcome this, LIGO and Virgo are located in isolated locations, away from human activity and natural disturbances. LIGO, for example, has 2 observatories, one in Hanford, Washington, and another in Livingston, Louisiana, to ensure that the signals detected are not local disturbances, but true gravitational wave signals. Virgo, which is located in Italy, works in conjunction with LIGO to create a 3-detector network, helping to pinpoint the source of the gravitational wave and confirm its validity. The first successful detection of gravitational waves came in September 2015, when LIGO detected a signal from the merger of 2 black holes. This event, known as GW150914, was the first direct observation of a black hole merger, and it confirmed Einstein's century-old prediction about gravitational waves. The waves detected came from 2 black holes, each about 30 times the mass of our Sun, merging into a single, more massive black hole. The energy released during the collision was equivalent to 3 solar masses, but it was released in the form of gravitational waves rather than light, making it invisible to traditional telescopes. Since then, both LIGO and Virgo have detected numerous other black hole mergers, as well as mergers involving neutron stars, the remnants of collapsed stars. These detections are not just confirming the existence of black holes, but also providing us with new data on the formation of black holes, the nature of space-time, and the behavior of matter in the most extreme environments. The discoveries made by LIGO and Virgo have revolutionized our understanding of the universe. Before gravitational wave astronomy, our knowledge of black hole mergers was limited to theoretical models. Now, we have a way to directly observe these events. These detectors are helping us answer questions about the formation of black holes, the role they play in galaxies, and the fundamental laws of physics that govern the universe. But the technology behind LIGO and Virgo is only improving. As the detectors become more sensitive and more precise, we will be able to detect even more distant events, such as mergers involving smaller black holes or even the first black holes that formed after the Big Bang. This next generation of gravitational wave observatories promises to open up even more exciting possibilities, allowing us to study the universe in ways we never thought possible. The future of gravitational wave astronomy holds tremendous potential as detectors like LIGO and Virgo are upgraded and new observatories are developed. These upgrades will enhance the sensitivity of existing detectors, enabling us to detect weaker and more distant gravitational waves. Currently, detectors can observe mergers that occur within a few billion light years, but as the sensitivity increases, we will be able to study gravitational waves from events much farther away, allowing us to observe the universe in ways never before possible. This means we'll be able to uncover the most distant, faint, and elusive signals from deep within the universe, possibly revealing new insights into its early stages. Upgrades like the LIGO A+ and Virgo Plus will enable us to capture signals from smaller black holes and other phenomena that were previously difficult to detect. These improvements will also allow us to study events from the early universe, including the first black holes formed shortly after the Big Bang. By observing these distant events, we'll gain a clearer picture of the cosmos' early stages, providing vital information on how black holes, galaxies, and stars formed and evolved from the cosmic dawn. Another exciting development is the launch of LISA, Laser Interferometer Space Antenna, a space-based detector that will expand our observational capabilities. Unlike Earth-based detectors, LISA will be able to detect lower-frequency gravitational waves that are difficult to pick up on the ground. By being in space, LISA will avoid environmental noise and will be able to observe more distant and powerful cosmic events like supermassive black hole mergers and the cosmic background from the Big Bang. This new perspective will allow us to explore the universe's most distant and mysterious events, shedding light on the origin and evolution of cosmic structures. With LISA, we will be able to observe mergers involving supermassive black holes, which are thought to play a key role in the formation and evolution of galaxies. These observations will give us critical insights into the development of the universe's largest structures. In addition, LISA will enable us to study cosmic evolution over billions of years, providing clues to how galaxies grew and evolved through time. It will also provide a detailed view of how supermassive black holes affect the dynamics of galaxies, shedding light on the complex interplay between black holes and the galaxies that host them. The evolution of gravitational wave detectors like LIGO, Virgo, and LISA will provide us not only with more data on black holes, but also help us understand space-time itself. Gravitational waves are ripples in space-time, and by studying these waves, we can test Einstein's theory of general relativity in extreme conditions. This will refine our understanding of gravity and the fabric of the universe at its most fundamental level. The observations of gravitational waves will also allow us to probe previously inaccessible regions of space-time, such as those near singularities in black holes, offering unparalleled insights into the nature of the universe. In addition to black holes, gravitational wave observatories will help us study neutron star mergers, events that create heavy elements like gold and platinum. Gravitational waves from these events provide valuable information about the processes that occur when neutron stars collide. Studying these waves will help us understand the creation of these elements, which are crucial for life on Earth. Furthermore, neutron star mergers may provide clues about the equation of state of ultra-dense matter, expanding our knowledge of nuclear physics and the fundamental properties of matter under extreme conditions. The technology behind these detectors is evolving rapidly. New techniques like machine learning algorithms will improve data analysis, enabling us to process signals more efficiently. These advancements will allow us to study black holes, neutron stars, and the nature of space-time with unprecedented detail. The improved ability to analyze data will help us answer some of the most fundamental questions in physics and cosmology, potentially unlocking new realms of knowledge about the laws that govern our universe. Gravitational wave astronomy is still in its early stages, but the potential discoveries are vast. As detectors become more sensitive, we'll gain new insights into black hole formation, galaxy evolution, and the fundamental nature of space-time. Each new detection brings us one step closer to unlocking the secrets of the universe, allowing us to study phenomena that were once beyond our reach. Gravitational wave astronomy is providing us with an entirely new way to explore the universe. By studying the ripples in space-time caused by the most violent cosmic events, we're uncovering new layers of knowledge about the cosmic landscape, the structure of the universe, and the forces that shape it. Gravitational waves offer a unique view of the universe that traditional astronomy cannot access. Light can be blocked or altered by matter, preventing us from observing certain cosmic phenomena. Gravitational waves, however, travel freely through matter, unaffected by gas clouds, stars, or objects in their path. This allows us to observe hidden events that were once unreachable, letting us peer deeper into space and time, reaching farther back into the history of the universe. One of the most exciting implications of this method of observation is the chance to study the formation of galaxies. The collisions of black holes and neutron stars detected through gravitational waves may play a significant role in galaxy evolution. As black holes merge, they release immense amounts of energy, affecting surrounding gas and stars. This energy might trigger star formation or influence a galaxy's overall dynamics. By studying these gravitational waves, we gain insights into how galaxies evolve, how black holes grow, and how these cosmic systems interact. Moreover, gravitational wave astronomy is reshaping our understanding of dark matter. Dark matter, which makes up about 85% of the mass of the universe, cannot be directly observed through light. However, its gravitational effects on galaxies and black holes provide indirect evidence of its presence. By observing how gravitational waves pass through different environments, scientists are building a clearer picture of how dark matter behaves and interacts with the rest of the universe. These observations might help us identify the nature of dark matter, an area that has long eluded researchers. The implications for cosmology are profound. Each new detection of gravitational waves offers the chance to test our understanding of space-time itself. Gravitational waves carry information about how space-time behaves under extreme gravitational conditions, allowing us to challenge Einstein's theory of general relativity. As we observe more mergers and collisions, we'll refine our understanding of how gravity works under such intense conditions, possibly leading to new discoveries that could alter our current understanding of the universe. One of the most intriguing aspects of gravitational wave astronomy is how it complements the study of cosmic inflation. Gravitational waves carry information from the universe's earliest moments, allowing us to study the cosmic microwave background, CMB, and the Big Bang. By detecting waves from the universe's infancy, scientists gain insights into cosmic inflation, the rapid expansion that occurred after the Big Bang. These observations help us understand the origins of the universe and the conditions during its first moments. The ability to detect and study these waves also opens the door to multi-messenger astronomy, where data from gravitational waves is combined with electromagnetic observations like light, radio waves, or X-rays. For example, when a gravitational wave signal is detected from a neutron star merger, astronomers can look for light emissions or gamma rays. This combined approach offers a much richer, more complete picture of cosmic events, improving our understanding of the processes involved. As we continue to observe gravitational waves, we will likely discover entirely new types of cosmic events. The universe is vast, and many phenomena remain unknown. Gravitational waves could reveal new sources of energy and matter, providing a fresh perspective on how the universe operates. Whether it's the discovery of a dark star, the merger of supermassive black holes, or an entirely new class of cosmic objects, gravitational wave astronomy is opening the door to countless possibilities. The potential for these discoveries to reshape our understanding of the universe is immense. Each gravitational wave detected brings us closer to understanding the forces and objects that make up the cosmos. We are at the beginning of a new era in astrophysics, one that offers deep insights into the nature of reality. Gravitational waves allow us to listen to the universe in ways we never could before, and each discovery is a step closer to unlocking the universe's deepest secrets. As exciting as the future of gravitational wave astronomy is, this field still faces several challenges that researchers must overcome to fully realize its potential. These challenges are both technological and conceptual, and addressing them will be key to unlocking the full power of gravitational wave observations. One major challenge is increasing the sensitivity of detectors. While LIGO, Virgo, and LISA have made groundbreaking discoveries, the precision required to detect faint gravitational waves is extraordinary. The signals we observe are incredibly weak and often masked by noise from Earth-based sources such as seismic activity, wind, and even human activity. This requires extremely sensitive instruments, capable of detecting displacements as small as a fraction of the diameter of a proton. As detectors like LIGO A+ and Virgo Plus are upgraded, the challenge will be to improve this sensitivity even further while minimizing the noise that could interfere with measurements. This will involve new techniques in both hardware and data processing. Another challenge is the limited sky coverage of current detectors. While LIGO and Virgo have made incredible strides, they have some limitations in detecting events that occur outside of their detection zones. To address this, more detectors are needed, both on Earth and in space. As more observatories such as LISA and future ground-based detectors come online, the network of gravitational wave detectors will expand. A larger network will allow us to detect events from all directions in the sky, improving the accuracy of measurements and enabling scientists to localize events more precisely. This will also lead to a more complete understanding of the universe, as more data from various perspectives will be available for analysis. Data analysis is another significant challenge. Gravitational wave signals are faint and often buried in noise, requiring sophisticated algorithms to detect and interpret them. As the detectors become more sensitive, the volume of data will increase dramatically, leading to a demand for advanced computational methods to analyze these signals. Machine learning and artificial intelligence, AI, are increasingly being integrated into the analysis process to help identify and classify signals more efficiently. However, these techniques still need to be refined to handle the complexity and scale of data from future observatories. On the conceptual side, one of the biggest opportunities lies in using gravitational waves to test our understanding of space-time and gravity. The extreme conditions surrounding black holes, neutron stars, and other massive objects provide a unique laboratory for testing the predictions of general relativity. As we detect more gravitational waves, we can learn more about how gravity behaves in environments where it is strongest. These observations could lead to new insights into the very fabric of space-time itself, and may even reveal areas where Einstein's theory needs to be revised or extended. Another exciting opportunity is the study of the early universe. Gravitational waves can carry information from the time shortly after the Big Bang, allowing scientists to probe the conditions that existed when the universe was just a fraction of a second old. By studying these primordial gravitational waves, we can learn about the processes that occurred during cosmic inflation and gain a deeper understanding of the origins of the universe. This could help answer some of the most fundamental questions about the nature of the cosmos, such as what triggered the Big Bang and how the universe evolved in its earliest moments. Multi-messenger astronomy is another area where gravitational waves offer enormous opportunities. By combining data from gravitational waves with electromagnetic observations, such as light, X-rays, and radio waves, scientists can get a more complete picture of cosmic events. For instance, when a gravitational wave signal from a neutron-star merger is detected, astronomers can search for corresponding electromagnetic signals such as gamma rays or optical light. This approach provides a richer, more detailed understanding of cosmic events, as gravitational waves offer information about the event's gravitational effects, while light-based observations reveal information about the electromagnetic processes. This combination of data sets is helping us study events in ways never before possible. The future of gravitational wave astronomy is full of exciting opportunities. As detectors become more sensitive and accurate, and as more observatories come online, we will be able to observe events that were previously invisible. This will open up new areas of exploration, from the formation of black holes and neutron stars to the evolution of galaxies and the nature of dark matter. The potential for groundbreaking discoveries is limitless, and each new detection of a gravitational wave brings us one step closer to understanding the most profound aspects of the universe. Gravitational wave astronomy is not just about technology and detectors, it's about global collaboration that drives the field forward. The discoveries made by observatories like LIGO, Virgo, and the upcoming LISA are the result of decades of combined efforts from scientists, engineers, and institutions worldwide. This international cooperation is key to overcoming the challenges of studying the universe's most extreme events. The need for international collaboration is fundamental to gravitational wave astronomy. LIGO operates observatories in the United States, Hanford, Washington, and Livingston, Louisiana, that work together to detect gravitational waves. Similarly, Virgo, based in Italy, collaborates with LIGO, forming a network that improves detection accuracy and helps pinpoint the source of gravitational waves. The combination of multiple observatories ensures reliable observations, minimizes false positives, and increases precision in measurements. These joint efforts improve our overall understanding of cosmic phenomena. This collaboration extends beyond observatories to research institutions, universities, and government agencies. Data collected by LIGO and Virgo is analyzed by teams across different countries, each contributing expertise in data processing, signal analysis, and astrophysical modeling. The pooling of resources and knowledge from around the world enhances the quality of research, accelerates discoveries, and allows scientists to tackle complex challenges in gravitational wave detection. A major milestone in this global collaboration is the LISA mission. LISA, Laser Interferometer Space Antenna, is a space-based detector that will complement the work of LIGO and Virgo. Unlike ground-based detectors, LISA will be able to detect lower-frequency gravitational waves, such as those from supermassive black hole mergers. The collaboration between ESA, European Space Agency, and NASA is a key example of international teamwork in gravitational wave research. LISA will open up new realms of observation, offering insights into supermassive black hole mergers, galaxy evolution, and the role of supermassive black holes in shaping galaxies. The success of LIGO, Virgo, and LISA would not be possible without the combined expertise from multiple countries. The technology behind these observatories is complex, and building, maintaining, and operating them requires shared knowledge and resources. For example, the precise laser systems used in LIGO and Virgo were developed through international collaboration, as were the techniques used to isolate the detectors from environmental noise. As the field progresses, continued collaboration will be essential for addressing new technical challenges and ensuring the precision and reliability of the detectors. The global network of detectors is also expanding. The addition of more observatories, such as those in Japan and Australia, will improve sky coverage and enhance the ability to detect gravitational waves from all directions. More detectors mean that we can observe events from multiple angles, increasing measurement accuracy and confirming signals, which reduces the likelihood of false detections. As more detectors join the network, the effectiveness of gravitational wave detection will continue to grow, providing a clearer picture of the universe. Gravitational wave astronomy benefits from global data sharing. The vast amounts of data produced by gravitational wave observatories require significant computing power and storage. By pooling resources, institutions can process the data more efficiently and verify discoveries faster. This collaboration allows the global scientific community to share in the excitement of new detections and provides a platform for researchers to contribute to the analysis, leading to quicker insights. This international collaboration also has broader implications. It encourages public engagement and education, as people from around the world follow the discoveries being made and learn about the science behind the observations. The global nature of this research means more people can participate in and benefit from these advancements, fostering a greater understanding of science on a global scale. Public interest in gravitational waves is growing, and this collaborative work helps make the field more accessible to people worldwide. The success of global collaboration in gravitational wave astronomy sets an example for future scientific endeavors. As more observatories come online and projects like LISA expand, international teamwork will continue to play a crucial role in pushing the boundaries of what is possible in gravitational wave research. The discoveries made through this cooperation will change our understanding of the universe, shedding light on black holes, neutron stars, and the very fabric of space-time itself. As gravitational wave astronomy continues to evolve, the next phase of research brings both exciting opportunities and significant challenges. The discoveries made so far have already changed our understanding of the universe, but the journey is far from over. The upcoming improvements in technology and the expansion of detection networks will enable us to learn even more about black holes, neutron stars, and the very fabric of space-time itself. One of the most significant opportunities in the coming years is the increased sensitivity of detectors. The current detectors, like LIGO and Virgo, have already made remarkable strides, but the next generation of detectors will be even more sensitive. Upgrades such as LIGO A+ and Virgo Plus will help detect weaker and more distant gravitational wave signals. This improvement will allow us to observe events that were previously invisible, including smaller black hole mergers and more distant sources, providing new insights into the universe's evolution. With enhanced sensitivity, we will be able to probe more subtle events and discover cosmic phenomena that are currently beyond our reach. The launch of the LISA mission, a space-based detector, is another major opportunity. Unlike the ground-based detectors, LISA will be able to detect lower-frequency gravitational waves, such as those generated by supermassive black hole mergers. By studying these signals, scientists will gain a better understanding of the formation and evolution of galaxies and supermassive black holes. LISA will complement the existing network of detectors, and together, they will provide a more comprehensive view of the universe. The collaboration between ESA and NASA on this mission demonstrates how international efforts are driving advancements in gravitational wave research. However, these advancements come with challenges. The increased sensitivity of detectors will lead to larger volumes of data, which presents a significant data analysis challenge. As the volume of data grows, the need for more sophisticated algorithms and machine learning tools will become critical. Researchers will need to refine these techniques to identify and interpret the weak signals amidst the noise. The use of AI and machine learning will be essential in processing the vast amounts of data efficiently and accurately, but the technology must continually evolve to keep pace with the expanding scope of the research. Another challenge is the noise that can interfere with the data. As detectors become more sensitive, even the smallest vibrations from sources like seismic activity, human activity, or environmental conditions could disrupt measurements. Researchers will need to develop more advanced techniques to isolate detectors from these interferences and ensure that the data they collect remains reliable. Innovations in isolation systems, as well as the use of remote locations for observatories, will be necessary to address this issue. The expansion of the gravitational wave network presents both opportunities and challenges. As more detectors are built, such as the planned observatories in Japan and Australia, the sky coverage will improve, allowing for better detection of gravitational waves from all regions of the sky. This will lead to more accurate measurements and the ability to triangulate the sources of gravitational waves more precisely. However, the increased number of detectors will also require better coordination and integration of data across observatories to ensure that the information gathered is consistent and accurate. International collaboration will continue to be essential as the field advances. The development of new detectors, the sharing of data, and the integration of different research efforts all rely on scientists and institutions working together. As the field becomes more complex and the number of players involved increases, maintaining effective communication and cooperation across borders will be crucial for the success of future missions. The work being done today sets the foundation for even more ambitious projects, and collaboration will be the key to unlocking the universe's deepest secrets. Gravitational wave astronomy also holds the potential to significantly impact other fields of physics. For instance, it could lead to a deeper understanding of quantum gravity and the nature of space-time. The observations of black hole mergers and neutron-star collisions provide an excellent test of Einstein's general relativity, and the data may uncover deviations from our current theories, opening up new avenues of research in fundamental physics. The potential for new discoveries is vast. As technology improves and the detection network expands, we will learn more about the most mysterious and extreme objects in the universe. Gravitational wave astronomy could unlock secrets about dark matter, dark energy, and the formation of the universe itself. Each new detection brings us one step closer to answering some of the most profound questions about the nature of reality. As gravitational wave astronomy progresses, the field is entering an exciting new phase, full of opportunities and challenges. The advancements in detector sensitivity, along with new observatories coming online, will offer a more detailed understanding of black holes, neutron stars, and the fabric of space-time. One of the most promising developments is the increased sensitivity of detectors. Current detectors like LIGO and Virgo have made incredible progress, but the next generation of detectors will be even more powerful. Upgrades such as LIGO A+, and Virgo Plus will allow us to detect weaker signals from more distant sources, including smaller black hole mergers and more subtle cosmic events. This will provide us with deeper insights into the universe's evolution and allow us to observe phenomena that are currently beyond our reach. Another game-changing advancement is the LISA mission, a space-based detector. Unlike ground-based observatories, LISA will detect lower-frequency gravitational waves, such as those from supermassive black hole mergers. By studying these waves, LISA will help us understand the formation of galaxies and the role supermassive black holes play in the evolution of the cosmos. LISA will complement ground-based detectors, expanding our understanding of the universe and offering new insights into the most massive objects in space. However, as detectors become more sensitive, there are new challenges. The volume of data will grow significantly, requiring advanced data analysis techniques to process and interpret the information. Artificial intelligence and machine learning will be crucial in efficiently analyzing vast datasets and identifying meaningful signals amidst the noise. These technologies will allow for quicker and more accurate discoveries, enabling scientists to explore the universe at an unprecedented scale. The expansion of the gravitational wave network will also be vital. New observatories, like those planned for Japan and Australia, will enhance sky coverage, allowing for the detection of gravitational waves from more regions of space. More detectors mean better measurements and more precise identification of events, which will reduce the likelihood of false detections and increase the reliability of findings. In addition to sensitivity and network expansion, multi-messenger astronomy will play an important role in future research. Gravitational waves will be studied alongside electromagnetic signals like light, radio waves, and X-rays to provide a more complete picture of cosmic events. By combining data from different observatories, we can gain deeper insights into the physical processes at play in events like neutron star mergers or black hole collisions. The future also holds the potential to explore the early universe. Gravitational waves from the Big Bang and cosmic inflation will provide clues to the universe's origins. Studying these waves will help us understand the first moments after the Big Bang and reveal how the universe evolved into its current state. This will bring us closer to answering some of the most fundamental questions about the nature of space, time, and the cosmos. As the field advances, the global collaboration will remain at the heart of its success. The development of new detectors, the sharing of data, and the integration of research efforts all require scientists and institutions to work together across borders. The growth of the field will depend on continued international cooperation, ensuring that the collective effort continues to push the boundaries of what we know about the universe. In the coming years, gravitational wave astronomy will also impact other fields of physics, such as quantum gravity and space-time. The data we collect from extreme events like black hole mergers will help us test theories of gravity and explore the very structure of the universe itself. The potential for new discoveries is vast. As technology improves and the detection network expands, we will uncover more about the most mysterious and extreme objects in the universe. Whether it's the formation of galaxies, the role of dark matter, or the secrets of black holes, gravitational wave astronomy will continue to push the limits of our understanding. Gravitational wave astronomy is not just transforming our understanding of astrophysics, it is also opening new doors in a variety of scientific disciplines. As we continue to detect and analyze gravitational waves, the impact on fields like fundamental physics, cosmology, and quantum mechanics is becoming increasingly evident. One of the most profound impacts of gravitational wave astronomy is on the study of general relativity. By observing the behavior of gravitational waves, we are testing Einstein's theory of gravity in ways that were never possible before. Gravitational waves offer a direct way to study the fabric of space-time, allowing us to probe the most extreme conditions of gravity, such as those near black holes. This provides us with an unprecedented opportunity to challenge or confirm predictions made by general relativity, and any discrepancies could lead to a new understanding of gravity, potentially paving the way for a more comprehensive theory of physics that incorporates quantum mechanics. Moreover, gravitational wave astronomy is revolutionizing our understanding of black holes and neutron stars. These extreme objects were previously observed only through indirect methods, such as X-ray emissions. But gravitational waves allow us to study their mergers and collisions directly, providing a wealth of information about their masses, spins, and other properties. This has led to groundbreaking discoveries, such as the first detection of a binary black hole merger in 2015. With more sensitive detectors and an expanding network, we can expect even more revelations about the nature of these mysterious objects. Another area where gravitational waves have a significant impact is cosmology. By studying the signals from the most distant gravitational wave sources, scientists can learn about the early universe and the formation of structures like galaxies and black holes. For example, gravitational waves can offer insights into the Big Bang and the cosmic inflation that followed, helping to answer questions about the origins of the universe and its early evolution. These findings may challenge or confirm existing models of the cosmos, potentially leading to a better understanding of how the universe began and how it will evolve. Gravitational wave astronomy is also providing a new window into the study of dark matter and dark energy. These mysterious components of the universe make up the majority of its mass and energy, but they have been extremely difficult to study directly. Gravitational waves offer a potential method to detect the gravitational effects of dark matter and dark energy. As the detectors become more sensitive, they may reveal new information about these elusive forces, helping us to better understand the true nature of the universe. Additionally, gravitational waves are contributing to the growing field of multi-messenger astronomy. By combining data from gravitational wave detectors with information from traditional telescopes and particle detectors, scientists can create a more complete picture of cosmic events. This interdisciplinary approach allows us to study events like neutron star mergers from multiple perspectives, leading to richer insights into their physical processes. The future of astronomy lies in the integration of different types of data, and gravitational waves are at the forefront of this new era. Another exciting possibility is the potential for quantum gravity breakthroughs. Gravitational waves could hold the key to understanding the quantum nature of space-time. By studying the properties of gravitational waves with high precision, scientists may be able to gain insights into the quantum structure of space-time itself, something that has long been a mystery in physics. This could ultimately lead to a unified theory of quantum mechanics and general relativity, bringing us closer to understanding the fundamental workings of the universe. The impact of gravitational wave astronomy extends beyond just physics and astronomy. It also has potential applications in technology and engineering. The highly sensitive detectors used to measure gravitational waves have driven innovations in laser technology, precision measurement, and data processing. These technologies can have applications in various fields, from medicine to materials science. As gravitational wave detectors continue to evolve, they will likely continue to spur advances in other areas of technology as well. As we move forward, the future potential of gravitational wave astronomy is immense. With improved detectors, such as the upcoming LISA and the growing network of observatories, the field will continue to push the boundaries of knowledge. The next decade promises to bring even more exciting discoveries, and gravitational waves will continue to shape our understanding of the universe in profound ways. As we enter the next phase of gravitational wave astronomy, the field promises to bring even more profound insights into the universe. With the development of next-generation detectors, the sensitivity of instruments like LIGO and Virgo will increase, allowing us to observe weaker and more distant gravitational wave events. These upgrades, such as LIGO A+ and Virgo Plus, will enable us to detect events that are currently beyond our reach, such as the merger of smaller black holes or neutron stars that are farther away. The launch of LISA, Laser Interferometer Space Antenna, will be another major leap. As a space-based detector, LISA will be capable of detecting lower-frequency gravitational waves, which are crucial for studying supermassive black hole mergers, the formation of galaxies, and even gravitational wave background signals from the early universe. Unlike ground-based detectors, LISA will operate in a different frequency range, providing complementary data to current observatories. This combination will allow scientists to study the universe from different perspectives and gain a more holistic view of cosmic phenomena. The growing global network of gravitational wave observatories will also significantly enhance our ability to detect and analyze gravitational waves. New observatories in Japan and Australia will help improve sky coverage and increase the ability to detect gravitational waves from different regions of the universe. This expansion will allow for more accurate triangulation of gravitational wave sources, leading to improved data on their location, masses, spin, and other characteristics. More detectors mean more data, and with that comes the potential for discovering new and unexpected cosmic events. While the increase in data will create opportunities for greater scientific discoveries, it also presents challenges. As gravitational wave detectors become more sensitive, the volume of data generated will grow exponentially. This requires advanced data processing methods to handle the increasing complexity of the signals. Machine learning and AI algorithms will be crucial in identifying relevant gravitational wave signals amidst a growing volume of noise. Researchers will need to continuously refine these tools to ensure they can keep up with the data, making real-time analysis more efficient. Another major opportunity is the ability to study the early universe. Gravitational waves can offer a direct probe into the Big Bang and the cosmic inflation that occurred shortly after. This process, when the universe expanded exponentially in a fraction of a second, remains one of the most significant unanswered questions in cosmology. By detecting primordial gravitational waves, scientists will be able to test different models of inflation and gain insights into the conditions that existed during the universe's infancy. This will allow for a deeper understanding of how the cosmos evolved into its present form. In addition to these advances, gravitational wave astronomy holds the potential to solve the mysteries of dark matter and dark energy. These elusive forces, which make up about 95% of the universe, have long been difficult to study directly. Gravitational waves could offer a new way to detect the effects of dark matter by studying how it interacts with other matter. In the future, we may even be able to detect gravitational waves from dark matter collisions, offering new insight into these fundamental components of the universe. The advancements in gravitational wave technology also have the potential to drive progress in other scientific fields. The laser interferometry used in gravitational wave detectors has applications beyond astrophysics, with implications for fields such as medical imaging, materials science, and quantum computing. The precise measurement techniques developed for detecting gravitational waves could be adapted for use in microscopy, navigation, and quantum sensors, potentially transforming a variety of industries. One of the most exciting aspects of gravitational wave astronomy is the interdisciplinary collaboration it fosters. As the field expands, scientists from various disciplines, including physics, engineering, computer science, and cosmology, will work together to solve complex challenges. The synergy between international institutions, space agencies, and research organizations will continue to drive innovation in technology and expand our knowledge of the cosmos. In the coming years, the field will continue to make groundbreaking discoveries that will reshape our understanding of space, time, and the universe. Each new detection brings us closer to answering some of the deepest questions in physics, cosmology, and beyond. The potential for new discoveries is vast, and the future of gravitational wave astronomy is poised to unlock many more mysteries of the universe. As gravitational wave astronomy advances, it's not only revolutionizing our understanding of the universe, but also shaping the future of scientific research across multiple disciplines. The field is fostering cross-disciplinary collaborations that are pushing the boundaries of technology, physics, and even our understanding of fundamental concepts like space and time. By pushing the limits of what we can observe, gravitational wave astronomy is driving new approaches to both theoretical and experimental physics. One of the key impacts of gravitational wave research is its role in inspiring future generations of scientists, engineers, and mathematicians. As more discoveries are made and the field continues to evolve, it is providing an exciting new avenue for students and researchers worldwide to engage in cutting-edge science. The complexity and potential of gravitational wave astronomy are opening doors for young scientists to explore the most extreme environments in the universe. This ongoing growth will ensure that the next generation of physicists, cosmologists, and engineers will continue to shape the future of our understanding of the cosmos. At its core, gravitational wave astronomy is deeply connected to theoretical physics and our quest for a unified theory of the universe. As we refine our understanding of gravity and space-time, gravitational waves offer an exceptional way to test the limits of Einstein's theory of general relativity. The field's ability to challenge our current models provides scientists with the opportunity to refine or even reshape the way we think about the fabric of space-time, quantum mechanics, and the relationship between gravity and quantum physics. These insights may ultimately help develop a theory of quantum gravity, which would be one of the most significant breakthroughs in theoretical physics. In addition to theoretical advancements, gravitational wave astronomy has a profound impact on experimental physics. The precision required to detect gravitational waves pushes the limits of measurement technology and sensor innovation. The cutting-edge detectors and laser interferometers developed for this field have applications far beyond astrophysics. They are being adapted for use in fields such as quantum sensing, medical imaging, and navigation systems, where precision is key. This knowledge transfer between gravitational wave research and other technological industries is a testament to the broader impact of the field. Another exciting aspect of gravitational wave astronomy is its potential to bridge gaps between fundamental science and applied technology. The tools developed to observe the cosmos are being adapted for practical use in a variety of fields. For example, the precision laser systems originally designed for detecting gravitational waves are now being applied to atomic clocks, GPS systems, and even biomedical applications, improving the accuracy and reliability of systems we rely on daily. These spin-off technologies underscore the broader societal benefits of basic scientific research and demonstrate how discoveries in one area can influence others. Gravitational wave research is also helping to unlock some of the mysteries of the universe, such as the formation of black holes and the processes that drive supernova explosions. These events are the most extreme and energetic processes in the universe, and gravitational waves allow us to study them in real time. By observing black hole mergers and neutron star collisions, we gain direct insights into their behavior, masses, spins, and other characteristics. This new understanding is reshaping how we view galaxy formation, stellar evolution, and the role these phenomena play in shaping the universe. As we continue to observe and analyze these events, we will be able to piece together more of the cosmic puzzle, shedding light on the origins of the universe and the forces that have shaped its evolution. Beyond the immediate advances in physics, gravitational wave astronomy is poised to impact society at large. As new discoveries are made, there will be greater public engagement with the science behind these findings. This growing interest will foster an appreciation for science, technology, engineering, and mathematics, STEM fields, encouraging more students to pursue careers in these areas. Public outreach initiatives and global collaborations will also increase awareness of the importance of funding for scientific research, highlighting how investment in basic science can lead to groundbreaking discoveries and practical innovations. In the coming years, gravitational wave astronomy will continue to make a lasting impact on both theoretical and applied science. As the field matures and more observations are made, we will deepen our understanding of some of the universe's most enigmatic phenomena. The field is also setting the stage for future technological breakthroughs and interdisciplinary advancements that will shape not only our understanding of space and time, but also how we interact with and navigate the world around us. Looking ahead, the potential for new discoveries is vast. As the global network of gravitational wave detectors grows, so too will our capacity to observe and analyze the universe's most extreme events. The discoveries made in this field will continue to push the limits of human knowledge and inspire future generations of scientists, engineers, and explorers to seek out new frontiers in the cosmos. The future of gravitational wave astronomy is increasingly intertwined with advancements in artificial intelligence, AI, machine learning, ML, and quantum computing. These technologies are not only driving innovation in the field itself, but are also revolutionizing the way we approach data analysis, signal detection, and computational models in a variety of scientific disciplines. Artificial intelligence, AI, and machine learning, ML, are crucial for the future of gravitational wave astronomy. The vast amounts of data generated by detectors like LIGO and Virgo are often noisy and complex, requiring sophisticated methods to identify meaningful signals. Machine learning algorithms, particularly deep learning techniques, are being employed to sift through this data more efficiently than traditional methods. These algorithms can learn to recognize the patterns in the data associated with real gravitational wave events, even from the smallest and faintest signals. The use of AI in gravitational wave astronomy is accelerating the detection process, helping scientists identify events in real time and providing faster, more accurate interpretations. In addition to improving detection, AI and ML are being integrated into the filtering process. Machine learning models are trained to distinguish between gravitational waves and other sources of noise, which can come from a variety of environmental and instrumental factors. These models continuously improve as more data is fed into them, leading to better performance over time. This development is paving the way for more sensitive and precise gravitational wave detectors, allowing us to observe even weaker events that were previously undetectable. Furthermore, the ability to process huge data sets generated by these advanced detectors opens the door for AI-powered simulations. Using machine learning techniques, researchers can simulate gravitational wave signals and their interactions with various astrophysical objects, providing new insights into the nature of black holes, neutron stars, and other cosmic phenomena. These simulations are increasingly accurate and can predict what gravitational waves might look like before they are observed, guiding the focus of detectors towards specific types of events. The role of quantum computing in gravitational wave astronomy is another exciting frontier. Quantum computers have the potential to process vast amounts of data at speeds far beyond what current classical computers can achieve. This could significantly improve the speed and efficiency of gravitational wave data analysis. Quantum algorithms are being developed to solve problems in signal processing, where traditional algorithms struggle to keep up with the increasing volume and complexity of the data. In particular, quantum computing could enable more efficient data matching and pattern recognition, which are critical tasks in gravitational wave astronomy. These tasks involve matching the detected signals with predicted models of astrophysical events, a process that requires immense computational power. As quantum computing technology matures, it will likely provide the necessary computational boost to analyze large data sets much faster, leading to quicker identification and more accurate modeling of gravitational wave events. Moreover, quantum technologies are also being explored in the development of quantum sensors, which could revolutionize the way we measure gravitational waves in the future. These sensors would utilize the principles of quantum mechanics to achieve unprecedented levels of sensitivity, improving the precision of future detectors. The fusion of quantum technology with gravitational wave astronomy could potentially lead to breakthroughs that will further enhance our ability to observe and study cosmic events with greater clarity. The intersection of AI, machine learning, and quantum computing is pushing the boundaries of what we thought possible in gravitational wave astronomy. These technologies are transforming how we process, interpret, and simulate the vast amounts of data generated by gravitational wave detectors. As the field grows, the role of these advanced technologies will only become more prominent, not just in gravitational wave astronomy, but across many areas of scientific research. The impact of these innovations extends beyond the confines of astrophysics. The advancements in AI, ML, and quantum computing, driven by gravitational wave research, are influencing industries such as finance, healthcare, and cybersecurity. For example, the algorithms used to analyze gravitational wave data are being adapted for fraud detection, medical diagnostics, and real-time financial forecasting. Similarly, quantum computing could lead to advancements in fields like drug discovery, materials science, and global cryptography. Looking forward, the integration of artificial intelligence, machine learning, and quantum technologies will drive not only advancements in gravitational wave astronomy, but also innovations across multiple sectors of society. The cross-pollination of these technologies will ensure that gravitational wave research remains at the forefront of technological progress, influencing how we approach some of the most significant challenges in science, engineering, and industry. As gravitational wave astronomy continues to evolve, the expansion of the global network of observatories will be essential to improving our understanding of the universe. The global collaboration between different countries, research institutions, and space agencies is key to increasing our sensitivity to gravitational waves and pushing the boundaries of what we can detect. Currently, observatories like LIGO in the United States and Virgo in Italy have provided groundbreaking discoveries, such as the first-ever detection of a gravitational wave signal from a black hole merger. However, to increase the precision of measurements and broaden our detection capabilities, it is critical to expand the network and have more observatories globally. The network expansion will allow for better triangulation of gravitational wave sources, improving the accuracy of identifying the locations of cosmic events. The addition of detectors in other countries is already underway, with upcoming projects in Japan and Australia playing an important role in this effort. The Kagra Observatory in Japan, for example, will soon be part of the global network, adding significant value to the detection of gravitational waves from the Asia-Pacific region. Similarly, the Australian detectors are expected to improve coverage of the sky and enhance the ability to pinpoint the exact origin of gravitational wave signals. This global network will allow scientists to detect a wider variety of gravitational wave events. More observatories means more chances to observe gravitational wave sources from different angles, making it easier to pinpoint their origins with greater precision. By improving sky coverage, we will be able to detect more distant events and capture signals from sources that were previously invisible to existing detectors. As the network grows, it will become more robust, ensuring that discoveries are made more quickly and more accurately. In addition to these new observatories, the LISA mission, a space-based gravitational wave observatory, will significantly expand our capabilities. LISA, Laser Interferometer, Space Antenna, is designed to detect lower-frequency gravitational waves, which are beyond the reach of ground-based detectors. Unlike terrestrial detectors, which are sensitive to higher-frequency waves, LISA will focus on supermassive black hole mergers and other large-scale cosmic events. The combination of space-based and ground-based detectors will allow for comprehensive observations across the gravitational wave spectrum, creating a holistic view of the universe. The success of these global collaborations depends on effective coordination and data sharing between observatories. It's crucial that researchers and institutions around the world continue to work together, sharing discoveries and resources to further the collective knowledge of the field. International collaboration will also be essential for addressing the technical challenges involved in building, maintaining, and upgrading the detectors, as well as analyzing the vast amounts of data generated by each observation. Moreover, the global scientific community is benefiting from the cross-pollination of ideas, knowledge, and expertise. Each observatory brings unique capabilities and technologies, contributing to the overall success of the global network. For instance, the experience gained from the advanced LIGO detectors has helped to improve Virgo, and future projects like Kagra and LISA will undoubtedly benefit from the knowledge gained by previous observatories. This cooperative spirit is a model for how scientific advancements are made, by pooling resources and expertise to tackle the greatest challenges. In addition to the direct scientific benefits, the expansion of the global network of observatories is also fostering public interest and education. As new observatories come online, the ability to detect more events means there will be more data to share with the global community. This data will not only drive new discoveries, but will also inspire the public and future generations of scientists to get involved in gravitational wave astronomy. Public outreach efforts will continue to grow, educating people on the importance of this research and the role it plays in our understanding of the universe. Looking ahead, the global collaboration in gravitational wave astronomy will continue to enhance the sensitivity and scope of observations, leading to more breakthroughs in our understanding of the cosmos. As the network of observatories expands, we will continue to make new discoveries that push the boundaries of physics and provide deeper insights into the universe's most mysterious phenomena. As we've seen throughout this journey into gravitational wave astronomy, This groundbreaking field is transforming how we explore the universe. From the first detection of gravitational waves to the exciting potential of future discoveries, we are on the verge of unlocking some of the most profound secrets of space and time. The advances in technology, particularly with next-generation detectors, artificial intelligence, and quantum computing, are not just enhancing our ability to observe cosmic events like black hole mergers and neutron star collisions, but they're also pushing the boundaries of scientific research across many fields. These innovations will continue to shape not just astrophysics, but other industries like healthcare, finance, and cybersecurity. But of course, none of this would be possible without the collaboration of scientists, researchers, and institutions across the globe. The expansion of the global network of observatories and the continued push for international cooperation will ensure that we continue to make major strides in our understanding of the universe. Looking forward, gravitational wave astronomy holds the promise of revealing even more about the mysteries of space-time, gravity, and the universe's origins. As we refine our tools and technology, there's no telling what incredible discoveries lie ahead. So, stay tuned, because the future of space exploration has never been more exciting. Thank you for watching. If you enjoyed this deep dive into gravitational waves, make sure to like, subscribe, and hit the bell icon for more content. And as always, let's keep pushing the boundaries of human knowledge together.